Hello and welcome to Module 3 of the course, which is Mathematical Methods for Theoretical Historians. And this is Lesson 3.1, which is an introduction, why mathematics works. So the new wave of theoretical history tends to be quite mathematical. And the question is, why is that? Why do we use mathematics? What do we get out of it? Well, there are two main reasons. So in theoretical history, we're looking for patterns. And that means we're collecting data. And so that leads us into the methods of data science and statistics so that we can analyze our data and understand what it's telling us. And secondly, we're trying to explain those patterns with models. And we're trying to be as precise and formal about our models as possible. And so that tends to lead us into mathematical equations. Because we then have to be very precise about what our variables are and what the connections between them are. So let's home in on the first of those to begin with, which is all about data. So one thing we might be interested in as theoretical historians is the rise and fall of empires. And part of that might be the durations of empires, how long they last. And that might be of interest because if we consider, for example, the United States as an empire, we might want to know whether it's living on borrowed time or whether it's got a long and glorious future ahead of it. So we want to know about how long should we expect empires to last. So what we might do is go out and get a sample of, say, 100 empires and measure their durations. And then we would plot the data on a chart. So we might get something like this. So we've got there a bar chart, a histogram, where the durations of the empires are along the bottom here, and the height of the bar represents the number of empires that lasted for that duration. So it might be that there was one empire that lasted 50 years, 3 empires that lasted 100 years, 6 empires that lasted 150 years, and so on. And with this pattern, we've got the familiar bell curve, or what's also known as the normal distribution, which is found, for example, in when we measure people's heights. Most people are around a typical average height, and there are very few very short people and very few very tall people. There's a definite average. So if we got something like that, we would say, right, there's a typical duration for empires, and it's very unlikely to last much longer than that or to be much shorter than that. But we might not get those kinds of statistics. We might get something different looking like this. So in this case, most empires last a short time. And for the longer the duration, the fewer the empires that there are. And we could, in this case, calculate an average. It might be somewhere around here. So these few but very long-lived empires would kind of balance out the many more short-lived empires, and we'd kind of get an average. But that average wouldn't really be that meaningful. It doesn't really tell us sort of what's typical for empires. It doesn't convey this impression that actually most of them will be very short-lived. And what might be of more interest here is how quickly this decays. How quickly does the chance of survival for a long time decrease? So with our this particular question of the durations of empires, we could get these different distributions, and we need those skills of statistics and mathematical skills of statistics so that we can recognize them and understand what we're looking at. We can say whether that's normal or this kind of distribution we can call an exponential distribution. When I come on to the lesson on statistics, we'll talk about these distributions in detail, so it doesn't really matter what, you know, precisely what this is about at the moment. It's just a label for this particular type of distribution. So yes, we need to be able to recognize what kind of distribution we're seeing in our data, because these distributions have different properties, and they have different ways of analysing them, and there are also different types of processes underlying that would generate these kinds of distributions. So if we have some knowledge of statistics, then we can start to understand what it is we're looking at in our data. And that's particularly so because, you know, in real life we may not get even a simple distribution like this. What we might get is something more like this. So this is a kind of sort of more messy thing that we might get in real life. The number of empires again, and duration. And we'll ask, well, you know, what is this? Is this a normal distribution? It's kind of look a bit like it. And is the reason it doesn't look exactly like a normal distribution, is it just because of a problem with the data? So, you know, we know that if we throw a die, we would expect to get a 6, one throw out of 6, one throw out of 6 times throwing it. But if we actually throw a die 6 times, then we might get 1 6, but we might get no 6s, or we might get 2 6s, or even more. So just by chance, we might get something different from the typical 1 in 6. But if we toss the die thousands of times, then yes, it will very reliably come out that on average 1 in 6 is a 6. So it might be the case here that yes, it is a normal distribution, but we just haven't collected enough data for that pattern, that distribution, to appear fully properly. And then there are statistical methods that can allow us to test that. We can say, well, with the data that we have, could this be caused by a normal distribution, and it's just, you know, a bit deviates from it just purely by chance? Or in fact, is this definitely not a normal distribution? And we might say, you know, could this actually be an exponential distribution, at least if we ignore the first 2? Let's say that, you know, the very short-lived ones don't really count, but after that it becomes an exponential distribution. Or it might be some combination of these, or it might be a completely different distribution altogether. This could be a Poisson distribution. A Poisson is another type of distribution. Again, it doesn't really matter for now. It's just a name, but we'll talk about these things when we come to the statistics course. So mathematics gives us the tools to answer questions like these. You know, what are we looking at here? How can we analyze this? What kind of processes might generate such a pattern? Another common situation we might get is when we're looking at the relationship between 2 variables that are of interest to us. So I'm going to take the example of crime in cities. So we might be interested in whether criminality increases with the size of a city's population. So that's the population of the city. And this is the crime per capita, the amount of crime per person. So obviously, if we, you know, increase the size of the city, we're likely to get more crime just because there are more people. But what we're interested in here, is do individuals become more criminal, more likely to commit crime in a larger city? And so we would take a lot of cities, we'd look at their populations, and we'd look at their crime statistics, and we might plot them on a chart, a scatter plot or an XY chart. And we might get something like that. And we could say, oh, well, you know, it certainly looks like there's some kind of trend here. It does seem that as the city population goes up, there's more crime per person, and so we might be tempted to draw a straight line through it. and say that there is a correlation between the per capita crime rate and the population of the city. But the question is this apparent correlation a genuine one? Could this actually just have occurred by chance? So statistics gives us the tools again to measure the quality of this correlation, and we can put kind of a percentages on it as to how accurate this relationship is, whether there's kind of a vague relationship but a lot of randomness, or whether it's a very clear and tight relationship. And that will depend on the amount of data that we have. So again, that's why we're going to need statistics, so that when we're looking at relationships between quantities of interest, we can test the quality of the apparent patterns, how real those patterns are. And now let's move on to the next thing. I said the other reason we're going to be sort of getting involved in mathematics is because we're trying to develop models to explain the patterns that we find, and that leads us into mathematics because we want to identify our variables, the things that we think are important, and we're going to develop equations to describe the relationships between those variables, how they affect each other. So if we take the example that we've just been looking at with per capita crime related to the population of a city, let's say we write the per capita crime rate as capital C, and we think that's correlated with the population of the city P. So we might say that the per capita crime rate C is proportional to the population. And this alpha symbol means is proportional to. And it really means it's strictly proportional to. So it means that if we double the population, then we will double the per capita crime rate. They vary exactly in relation to each other. And in fact, I won't though use that proportional sign very much in this course. I will be more likely to use this squiggle, which means more that per capita crime rate depends upon the population. It varies with the population, but we're not saying precisely how it varies. So we're not committing to saying that double the population, you double the per capita crime rate. It could be the per capita crime rate depends on the square root of the population or something like that. So we're just saying that it depends in some way on the population, but not necessarily strictly proportional to. Now that said, in fact, 9 times out of 10 when I use this symbol in this course, I will be talking about strict proportionality. But that will become apparent from the context. But I tend to prefer that squiggle sign as sort of less of a commitment to saying it's definitely a strictly proportional relationship. Now we might say that per capita crime rate depends on population, but that may not be the only thing it depends on. It might depend on the level of poverty in the city. So if people are poorer, they're more likely to steal things, for example. So we might say that per capita crime depends not just on population, but here I'll use the term not poverty because poverty begins with a P and we already got a P for population. I'll say economic hardship, in other words and the economic hardship, which I'll represent with the capital H. So per capita crime rate depends on economic hardship, and let's actually make this a proper equation. We'll put an equal sign there, and let's say it equals the economic hardship multiplied by the population. So this says that if the economic hardship increases, then the per capita crime rate increases, or if the population increases, the per capita crime rate increases. If both increase, increase even more. So so it depends on both of them, and they're multiplied together. So now we've got a mathematical equation describing our theory about what per capita crime rate depends upon. And then we could take this equation and get some data and see, on per capita crime rates and economic hardship and population size for a whole range of cities through history, or for a particular city over time, and see if this relationship holds up. And if we find that indeed the patterns that we see in the data are explained by this relationship between the variables, then we can say, well, that seems to be a pretty good model, and then we can use that to predict how the per capita crime rate may vary in future with fluctuations in the economy, let's say. So to summarize, as theoretical historians, we're going to get involved in mathematics because we're looking for patterns, or we're looking at patterns. So we've got data which necessarily gets us embroiled in statistics, and with the statistics we're then confirming the existence of patterns. So it looks like the durations of empires fit a normal distribution. With statistics we can prove whether it does or does not. We can confirm the existence of patterns, or these two variables seem to be related. With the statistics we can tell whether or not that is a real correlation. And then the other aspect is the models, where we're getting into equations, and that is explaining the logic behind the patterns, why those patterns are what they are, what the variables are, and what the relationships between those variables are that generate these patterns we've seen in the data. Now, this doesn't mean, though, that we need to become mathematical geniuses. So when you're looking through a paper and you see equations in it, you don't need to feel that you're failing if you can't see that, look at that equation and immediately see what it means. Because an equation packs an awful lot of information into a very compact space. So you can't read an equation like you can read English. And I, myself have had the experience of looking back at papers that I've written that involve mathematical equations, and I can't see immediately what I was doing or how that works, and it's something I've written myself. Now, I'm not a mathematical genius, but someone who is a mathematical genius is Professor Roger Penrose, who's Professor of Mathematics at Oxford University. He was actually the PhD supervisor for Stephen Hawking. So, and he was the PhD examiner for Stephen Hawking, and he spotted a mistake in Stephen Hawking's PhD thesis. So Stephen Hawking is a genius, and Roger Penrose is better than that. But even Roger Penrose, as a professor of mathematics, he says that when he reads a paper, he just skips over the equations. He just reads the text, reads the interpretation. And so, that's what we should do when we're looking through theoretical history papers that have equations. We can just skip over the equations and just read the writing around it to understand what's going on and get the gist of it. But we still need some kind of mathematical skills so that we can sort of have a feel for what's going on, particularly because the text may mention the mathematical methods that are being used and may quote some statistics, for example. So we don't need to have a look in detail at how they got those statistics, but we need to understand when they quote those statistics what those mean. And the only reason we would want to go back and look at the equations in detail is if we are particularly interested in the paper. You know, we think, oh gosh, you know, this looks really good. I think I could build on this. So I really want to try and understand exactly what they're doing and how their mathematics works, so I can maybe extend it in certain ways or adapt it to my own ideas and work. Or it might be because we're actually dubious about the paper. We think, you know, well, this doesn't really sound right. Let's have a look, you know, drill into their maths and see if it's really genuine. You know, maybe they've made some errors or something, or, you know, let's find out how reliable really their conclusions are. So yes, so, you know, you don't need to feel you need to understand every single equation as you go through something, but you need to have enough of a feel for the mathematics that you can sort of keep up with what's going on. Now let's go back and have a look at that equation I put up earlier. We have this: the per capita crime rate is equal to the economic hardship times the population of a city. Now this isn't a real equation, it's just, you know, something I've made up just to illustrate the point. But someone might look at that and say, oh, you know, come on, something as complicated as crime, per capita crime, and something as complicated as poverty, economic hardship, you know, it's not going to be related by a simple equation like this, just multiplying the things together. But in fact, yes, there are reasons why we should expect our equations in theoretical history or anywhere else to be quite simple. Just involve, you know, typically multiplying things together. And that's because we get the same kind of thing in physics. So let's take E equals mc squared. This is saying that the energy in a particle is equal to the mass of the particle multiplied by a constant, the speed of light squared, c representing the speed of light. So this is we're saying in the theory of relativity, which is a very complicated theory, that the energy depends on the mass. But the algebraic equation that describes that is very simple. In fact, it's the simplest possible way it depends on it. The energy is just proportional to the mass. Double the mass, you double the energy. You know, the more mass, the more energy there is. It's the simplest possible relationship, despite the complexity of the underlying theory. And we find this in all sorts of physics equations. You know, it's absolutely typical. The variables always tend to be just multiplied together, or we might have a square, or we might have a square root. But, you know, they tend to be simple multiplications, simple powers, or simple roots of the equations. And the reason for that is what I will call dimensional balancing. So dimensional balancing, in equations they have to be dimensionally balanced, and that forces them to be simple. So let me explain what that's all about. But before we do that, I'm going to do a bit of a review of the mathematics of exponents, or the mathematical notation of exponents. So you know, many people may understand this well, so you know, but this is like a review for those people who may not be up to speed. So this is just a bit of an aside. So exponents. Well, let's take a variable x, and we might be interested in what happens when we've got x multiplied by x. And we can write that as x to the power of 2. This just means we multiply x by itself twice. So we've got x times x. There are 2 x's. So there's nothing very profound about this. You know, it's not proving anything. It's just a shorthand. It's just a notation. It's just a way of writing things. Instead of laboriously writing out x times x, we can just write x to the power of 2. So this is the exponent, or sometimes we call it the index. So x times x equals x squared. That's just a simple way of writing it. And then we might have x times many times x, and let's say there are n x's multiplied together. Then we write that as x to the power of n. The exponent is n. And so with this x on its own here, we could write that as x to the power of 1, because there's just one x. Now my mother tells me that, you know, when she was studying mathematics at school, the teachers were always talking about this thing x, and she always had this question, well, what is x? You know, what is this x you're talking about? And so that was a mystery to her. So if you're like that, this x is just a placeholder. It just means it could be anything. It's just a way of describing this notation. So this could be 3, for example. If it were 3 times 3, that would be 3 squared. Or x could be 10. If we got 10 times 10, that's 10 squared. That's the way we write it. So that's all, you know, there's all we're saying with x is it's just a placeholder for, it means substitute anything in here. Now, suppose we have an x to the power of m multiplied by x to the power of n. What will that be equal to? Well, we've got m x's multiplied together here and n x's multiplied together here, and we're multiplying all that together. So there's going to be m x's and then n x's. So in total, there's m plus n x's being multiplied together. So that's going to be x to the m plus n. What about if we had x to the m itself to the power of n? Well, this means we've got x to the m, and we're multiplying those times together n times. So there's m x's in that, and then we've got n lots of m x's. So that's going to be n times m. There's m, m, m. There are n of those, so it's m times n x's in all. So x to the m to the power of n is equal to x to the mn. Now consider the square root of x. Well, I'll just tell you that that is written as x to the power of a half. And we can see why that is, because if we take the square root of x and multiply it by itself, then, you know, by the definition of the square root, that is just equal to x. X is root x times root x. But now I've told you that root x is written as x to the half. So that is x to the half times x to the half. And then by this rule here, to the half times a half is going to be a half plus a half. So that's x to the half plus a half. And a half plus a half is 1, so that's just equal to x to the 1, which is x. So that is correct. You know, x, does indeed come out as x. So that shows that writing this as x to the half is correct, and it makes sense, and it's the right way to do it. And if we've got then the nth root of x, so it might be the cube root, for example, that would be x to the 1 over n. So if it were the cube root, then would be 3. This would be x to the 1/3, and so on. And then in general, if we've got something that is written as x to m over n, that is equal to the n on the bottom here means we've got the nth root, and the m on the top here means we've got just x to the m. So x to the m over n is the nth root of x to the m. Now another thing we need to know is that x to the 0 is equal to 1. Doesn't matter what x is, to the power of 0 it's always just 1. And again, we can sort of check why that is consistent and why that makes sense. If we take, say, x squared times x to the 0, then again by this rule that's going to be x to the 2 plus 0, which is just equal to x to the 2, because 2 plus 0 is just 2. So x squared times x to the 0 equals x squared. So this must be 1, because it's when you multiply something by 1 that it just leaves it unchanged and just gives you what you started with. The next thing we need to know is that if we've got 1 over x, 1 divided by x, that is written as x to the minus 1. And let's just check the consistency of that, see why that works. If we've got x times 1 over x, well, x times 1 over x, the x's cancel, that's just going to be equal to 1. X divided by x is 1, whatever x is. Now, x times 1 over x, well, that's x to the 1 times, I've just said 1 over x is x to the minus 1. So that's going to be x to the 1 minus 1. We add them together. So that's 1 plus minus 1. Well, 1 minus 1. And so that is equal to x to the 1 minus 1 is 0. And indeed, x to the 0 is 1, which we said here. So 1, it should be 1, and indeed it is 1. So if we write 1 over x as x to the minus 1, then this all works. So that is why 1 over x is x to the minus 1. And then we can have, lastly, in general, 1 over x to the n. That would be x to the minus n. So 1 over x squared, x to the minus 2. So that's just a recap of how mathematical exponents work. And we're going to be using that now as we talk about the issue of dimensional balancing of equations and dimensional analysis. So that's the end of that aside. Okay, so dimensional balancing, dimensional analysis. In physics, we have certain fundamental quantities or fundamental dimensions. And 3 of them are length, time, and mass, L, T, and M. 3 fundamental dimensions. And the point about this is that other quantities that we might meet in physics can be expressed in terms of these fundamental dimensions. So if, for example, we have a distance, then, well, that is a length. So that has just got a dimension of L. But if we have an area, the formula for an area is the breadth times the height. So it is 2 lengths multiplied together. That length multiplied by that length gives you the area. So area has the dimensions of L times L, or in other words, L squared. And of course, that's why we call it L squared, because it's taking a variable and multiplying it by itself gives you an area, gives you a kind of a square, because it's equal on both sides. And then if we take a volume, the formula for volume is the length times the breadth times the height. So that is 3 lengths multiplied together. So the dimensions of volume is L cubed. So with this fundamental dimension, we can express the dimensions of these quantities, area and volume, in terms of that fundamental dimension. Now let's take the example of speed, the speed of something. So I'll have here, there's a car that's travelling along the road. and it goes a certain distance, and here's, you know, a stopwatch. It takes a certain time. The formula for speed is the distance divided by the time. You know, it's miles per hour. How many miles distance did you go per hour, per time? So it's the distance divided by the time. And then in terms of our fundamental dimensions, the distance is a length, and time is, of course, a time. So the dimensions are a length divided by a time, which we can write as, using our exponent notation, LT to the -1. And then what about acceleration? So let's take an example of a car moving down the road, and there it is. And we'll say that to begin with, it's going at 20 miles per hour, and later it's going at 30 miles per hour. So it's sped up, it's accelerated. And in fact, the change, there's an increase of 10 miles per hour in the speed. So that's a change of the speed. And then the question is, how long did that take? Well, let's just keep things simple and say this is take an hour. 1 hour, let's say. So that would then be 10 miles per hour per hour. We've increased by 10 miles per hour in an hour. 10 miles per hour per hour. So the formula for acceleration, which I'll write like that, is equal to the change in the speed divided by the time taken. Now the change in the speed, well, it was here an increase of 10 miles per hour. So the change in the speed is just another speed. 10 miles per hour is a speed. So, you know, it's just, it's a change in speed. In other words, it's just a speed divided by a time. And we know what the dimensions of speed are. We just worked them out. They're LT to the -1, and then time t. So we've now got another t on the bottom, which is a -1 again. So we've got 1 -1 and another -1, so that's LT to the -2. So the dimensions of acceleration are LT to the -2. And this leads to the idea then of the dimensional analysis of an equation. So let me take you on to that. So in physics, people are interested in pendulums, and a pendulum has a certain period, which is the time taken to go from one side to the other and back again. That's the period of the swing, the period of the pendulum. And the period depends upon the length of the pendulum. So if we shorten the length, it swings more quickly. And it also depends on what we call the acceleration due to gravity. If gravity were weaker, it wouldn't pull it back so quickly to the centre, so it would be slower in its swing. Whereas if gravity were stronger, you know, it'd be pulled back very quickly to the centre and it would swing more quickly. So the period of a pendulum depends on these two things. There's our pendulum. Depends on the length of the pendulum as it swings back and forward, and it depends on this acceleration due to gravity. which we write as little g. So if we write down the equation, I'll use P for the period of the pendulum. It's actually more conventional to write the period of a pendulum with a capital T. But because we're using capital T for the dimension of time, to avoid confusion, just write P for period. The formula is it's 2 pi times the square root of L, the length, divided by G, the acceleration due to gravity. And now we can do a dimensional analysis of this equation. So let's first look at the left-hand side. What are the dimensions? Well, it's the period. The period is just a time. The period is 10 seconds or whatever it might be. So that has the dimensions of t for time. What about on this side? Well, 2 pi, well, that's just a number. 2 pi is, around about 6. So it's not 6 anything, it's just a number 6. It's not 6 centimeters or anything, it's just 6. So it doesn't have any dimensions. But for this, we've got L is a length, and then G is the acceleration due to gravity, and we've seen now what the dimensions of acceleration are. They're Lt to the minus 2, and then that is we take the square root of that, so it's to the power of a half. And we can now simplify this. So firstly, we've got L on the top and L on the bottom, so we can cancel those. So that gives us 1 over t to the minus 2 to the half. Now 1 over something is the minus of it. So we've got t to the minus 2, well, it will be t to the minus 2. And minus minus, a double negative, is just back to positive. So this becomes just t to the power of 2, t squared. And we're still taking that to the power of a half. And now using our other exponent rules, this becomes t to the 2 to the power of a half is going to be t to the 2 times a half. And 2 times a half is just 1. So this is equal to t to the 1, which is equal to then just t. So the dimensions on this side are also time, t. And that makes sense, and it ought to be like that, because you're comparing here the period with this thing. Well, you can only compare a time with another time. You can compare the time it takes to boil your egg in the morning with the time it takes you to get dressed. Those are 2 times, and one can be shorter or longer than the other. But you can't compare the time it takes to boil your egg with the height of your house. It doesn't make sense. You can't say the time to boil my egg is shorter than the height of my house. That's meaningless. So it should always be that the dimensions on one side of an equation are the same as the dimensions on the other side. If they're not, then there's something wrong with your equation. And it's because of this dimensional balancing that we must have the same dimensions on each side. It tends to require us to get simple relationships between the variables so that they will cancel out like this. So, for example, we couldn't have an equation that for the period of a pendulum that looked something like this, that it was 2 pi times L to the 2.71 over G to the 1.98 all to the power of 0.31, because if we tried to simplify that, it wouldn't cancel down and end up with a time on this side. It would be some time, something completely different. It would have L's and T's, and it wouldn't match that simple time. Now, it could be that if you choose these numbers correctly, then you might be able to get them to cancel down. But that's not very likely. The equations are much more likely to work with simple numbers here, and so that is why in physics anyway we tend to see these simple equations, because the dimensions on both sides have got to balance. So we're not raising them to weird and wonderful powers. They're going to be simple powers. So things will be multiplied, they'll be divided, maybe we'll be taking the square root as we did here, or maybe we'll be squaring it, maybe cube, but it will always be something relatively simple, so that things cancel and we come back to the dimensions that they ought to be. And this works in physics, but it should also apply in theoretical history. Now, we don't know what necessarily the dimensions are in theoretical history. I don't think anyone's particularly defined those yet. But we should find in theoretical history that there are certain fundamental dimensions, and we need those to balance on different sides of an equation, and that will force our equations to be relatively simple, like C equals H times P. We're not going to get it depending on strange powers up here, because otherwise there would not be a dimensional balancing. So just to repeat myself, that we would expect our equations in theoretical history to look simple. And I'm going to finish off just by going through what the next lessons in this module are. So I divide the module into 7 more lessons. So the next one, which will be lesson 3.2, is going to be all about calculus. So calculus is a way of studying changes, rates of change in variables. So with calculus, we're looking at basic dynamics, how the rates, or how one variable changes as a function of another, how the rate of change of one variable depends on other variables. So it's basic dynamics. The next lesson will be about scale-free phenomena. Now, I mentioned these in an earlier module, I think it was module 1, scale-free phenomena, where things that look the same on different scales. If we look at it on the large scale or the small scale, it looks the same. If we zoom in, it looks the same as if we zoom out. It's things that contain copies of themselves, smaller scale copies of themselves. And these are very common in socio-historical systems. So they're kind of is a characteristic pattern in socio-historical systems. And so it makes sense to separate those out and have a lesson devoted to understanding the properties of scale-free phenomena and how we can analyze them. The next lesson is going to be about nonlinear dynamics. So these tend to be systems whose equations are too complicated for us to solve exactly. We can't get a precise formula to describe how the system behaves. But we see the behaviors of that are sort of grouped under the term chaos, and also complexity science. And here we may not be able to solve the equations, but there are techniques for analysing the properties of the systems without solving the equations, but extracting some information about their behaviour. And so we will discuss what those techniques are. And, you know, we certainly expect chaos and complexity in socio-historical phenomena. The next lesson will be all about networks. So, networks, just things that are connected, and we expect to find networks in socio-historical systems. I mean, people are connected in networks. You know, you interact with your friends who interact with their friends, and we form these social networks. Or this might be cities, a network of cities joined by roads, or perhaps more abstractly representing economic flows between cities. So they are connected in a network through their economic interactions. And there's a whole science of networks, which allows us to sort of analyse the properties of networks. And as I said, these could be people or cities. So we will look at network science, what it's got to bring to social networks and economic networks. The next one will be all about computational methods. Computational methods. So it may happen in the kinds of systems we're going to look at that the equations describing the system are so large in number, there's so many of them, that we can't actually solve them. But what we can do is feed them into a computer and run a computer simulation based on those equations, and then watch how the system behaves. So this is talking about basically computer simulation. So, you know, it might be something like the computer game SimCity, where you're the mayor responsible for planning a city, and you've got a whole range of variables, you know, like your budget and how much of your budget you spend on the roads versus on building programs, how much tax you raise, and so on. So you've got all these variables, and there's a large number of equations connecting them all. The computer simulates, runs them forward in time, rather than finding a sort of exact formula for everything. It steps through. And you may sort of propose some equations and then run your simulation and then compare the output with what you see in reality and see whether you know, if it matches it, fine, but if it doesn't, think about how you might change and adjust those equations to adjust the behavior of the system. So that's computational methods simulation. And as you know, the game SimCity or the Civilization games show that simulation, you know, is very relevant to studying social and economic and historical phenomena. The next lesson will be statistics. So, you know, so we've seen at the beginning of the lesson, you know, why statistics is going to be important to us. So we'll, in discussing statistics, we'll talk about things like statistical distributions and testing correlations between variables, you know, working out whether correlations are real or how real they might be. And then lastly, lesson 3.8 is going to be about time series analysis. So a time series is a variable that changes over time. time. And so this might be, for example, a stock market price, the stock market index, or the price of an individual share, and we might get something like this. That's a time series. It might be also something like war, the incidence of war, so that over time there was periods when there was a lot of war and more peaceful times. And the kind of question we're going to have when we look at a time series like this is there a regular oscillation? Does this go up and down? It kind of looks like there might be a regular oscillation. Well, is there one? Time series analysis is going to be able to help us test whether there is indeed a regular oscillation, or it might be two or more oscillations superimposed on each other. That will be time series analysis. So that's 7 more lessons, and within each lesson there will be multiple parts. So there will be this will be several lectures, each one of these, 1 lecture per part and multiple parts per lesson. So as you can see, we've got an awful lot to get through here.